Here we discuss the source term. So recall the vorticity equation. And remember, there are two terms which we're used to see in a conservation equation. That is this term which represents the advection, this term which represents the diffusion of vorticity. So those, if you only had these, vorticity would be conserved. But in the vorticity equation, you have this additional term here, which I'm going to call a source term, because this is a term which will generate vorticity. Right? So if this term here is non-zero, then vorticity will be created inside of the flow field. So you will have additional vorticity resulting from this source. Remember that the source term is always zero in 2D flows. And what that tells you is that in 2D flows, you never create vorticity in the bulk of your flow. So inside of the flow, you never create vorticity. The only place where you can create vorticity in a 2D flow is at a boundary. So at a no-slip boundary, you can create vorticity, or if you assume that you have vorticity coming from infinity. But in a 2D flow, you never create vorticity in the bulk of the flow. So inside of the flow, far away from the boundaries, you never create vorticity. Vorticity is conserved. It can either come inside of your main because it's advected, or it can come somewhere because it's diffused from a place where it was already there, but it's not created. Okay, so we will not discuss the source term in much detail. You would see that more in a turbulence class or in a class on vorticity, but I want to give you a little bit of a feel for what the source term is, and for that we will assume that we will neglect the diffusion term and just think about the advection term and the source term, right? And so you see here directly that if this term is non-zero, then there is net vorticity created as you follow. If you follow a material element, vorticity can be created and can be added because of this term here. And there is oftentimes two ways of thinking two terms to separate in that vorticity term. Remember, this brings us back to the very early discussion, but this is a omega grad u term. So this represents, this would be the gradient of the velocity field projected in the direction of the vorticity, right? So this is how does my velocity vector change if I'm moving in the direction of the vorticity vector. And so one way of writing this term, right, is really, if we think about the flow, and now I'm not representing a streamline, but so the streamline might go like this of the flow. So this is completely irrelevant here, because we're going to look at the vorticity lines. And so if for instance here, let's say this is my vorticity vector at this point here, then I can follow a line of vorticity. I don't know exactly, so this will be a vortex filament. It's not going to be in the same direction of the flow. So this is here would be a vortex filament. And I'm going to call the direction of the vortex filament the direction S. So if I'm at this point, this here is going to be my direction S. And then we have two directions which are normal to S, and I'm going to call these N and M, but it doesn't really matter which these are for this discussion. So S is the direction of the vorticity vector, okay? And therefore this term here, I can rewrite that as really omega, the value of, so omega S here is going to be my vorticity vector dot the gradient of u. So really I'm looking at omega, this term is omega, the value of omega times S grad u. And so this is how my velocity vector changes in the direction s. Now my velocity vector has component in the s, n, and m direction, so I can rewrite this term as omega partial s of my velocity vector, which has a component us in the s direction, plus a component un in the n direction, plus a component um in the m direction. Okay? And so essentially there are two terms that I want to focus on. It's this term here, the term in the s direction, right? So that is one term, one source term for vorticity. So you can create vorticity if dus ds is non-zero. And what would dus ds represent? That would represent a linear strain, so an elongation. That would be a linear strain in the direction of the vorticity. This linear strain rate really represents a stretching. So if the flow field is such that you stretch a vortex filament, then you create additional vorticity. The second term that can create vorticity is the following. So if we look now not in the s direction, but we're looking in the direction normal to the vorticity, we have partial us partial n, partial un partial s, partial un partial s, and that somehow represents a shear. This is you see that the direction of the derivative is different than the direction of the flow, and that represents a rotation. So if the flow field is such that you have a rotation or tilting in the direction of the vorticity filament, then you create additional vorticity. So this here is the vorticity created because of the rotation or the tilting of a vortex line. Again, keep in mind that these two terms don't exist in a 2D flow, they only exist in a 3D flow. And therefore you will see that in another class in more details, but there are two mechanisms by which you can create additional vorticity inside of a flow, and that is by vortex stretching. So if you have a linear strain rate in the direction of the vortex filament, or vortex tilting. So if your vortex filament is rotated, then you create additional vorticity.